Deep down inside a secure Parisian archive, there are historical laboratory notebooks stored safely inside thick, lead-lined containment boxes. Researchers today must sign a liability waiver and put on protective gear just to read her handwriting. The pages themselves are still highly radioactive. To understand why, we have to look back to the scientific baseline of the 1890s. In 1896, Henri Becquerel observed that uranium salts spontaneously emitted mysterious, invisible rays that could fog up a photographic plate. Most of the scientific establishment saw this as a minor quirk of uranium, but a young physicist named Marie Curie suspected these rays were evidence of a broader physical law. Her suspicion centered on a dark, heavy ore called pitchblende. Pitchblende emitted radiation at levels 4 times higher than its pure uranium content could mathematically account for. To explain this, Curie argued this energy, which she named radioactivity, was an intrinsic property of the atom itself, firing directly from the core. Because radioactivity is tied directly to the atom, that extra energy in the pitchblende had to come from somewhere. Her second hypothesis was that the rock contained entirely new, undiscovered elements. Proposing the atom as a powerhouse of energy meant she couldn't rely on theoretical papers. She had to crack open the rock and physically extract the invisible elements hiding inside. Her primary tool for tracking this energy was a highly sensitive electrometer, built by her husband and collaborator, Pierre Curie. Together, they processed thousands of kilograms of pitchblende by hand inside a drafty, makeshift shed in Paris. Her central methodology relied on a chemical process known as fractional crystallization. The schematic shows how it works. You dissolve the raw mineral in acid, boil the liquid to evaporate it, and then allow the remaining material to cool. Because different elements have different solubilities, they form crystals at different times. She would then use Pierre's electrometer to test which batch of newly formed crystals was the most radioactive. She kept the active ones, threw out the rest, and dissolved them again. Watching this cycle repeat, you can see the reading spikes higher with every successful separation. It was truly a punishing physical sieve. This manual labor was the only way to sift through mountains of useless rock and find a substance no human had ever seen. This intense separation eventually yielded 2 highly radioactive fractions. She named them polonium, after her native Poland, and radium. But in chemistry, discovering a radioactive substance isn't enough. For an element to officially exist and take its place on the periodic table, its atomic weight must be precisely measured. Look at these original data tables published in France. To get these measurements, Curie processed tons of raw ore to isolate just 0.4 grams of perfectly pure radium chloride. From that tiny sample, she determined radium's atomic weight to be exactly 226.2. As we see this blank tile fill in, that precise mathematical proof is what cemented radium as a new element. She took a mountain of ore and through sheer physical endurance, reduced it down to a fraction of a gram of pure truth. By 1911, Curie shifted from proving radium existed to standardizing how it was used, preparing the first international standard measurement for the element. She realized that radium's continuous radiation had a profound effect on human tissue. Specifically, it could be targeted to destroy malignant, cancerous cells. Hospitals began harnessing her discoveries, adopting the Curie therapy method to treat malignant tumors with localized radiation. But the outbreak of World War I required Curie to scale her medical technology rapidly for battlefield logistics. She raised funds to create the Petite Curies, a fleet of 20 mobile X-ray vehicles. She equipped these vans herself and drove them directly to the front lines, helping surgeons quickly locate shrapnel and shattered bones in the wounded soldiers. The exact same subatomic energy she had coaxed out of pitchblende in a cold Paris shed was now deployed globally, saving thousands of young men from unnecessary amputation or death. Her rigorous methods earned her 2 Nobel Prizes. She was the first woman to win the award and remains the only person in history to win in 2 different fields, physics and chemistry. She also founded the Radium Institute in Paris, which became a leading global center for the study of radioactivity and clinical cancer treatment. But we return to those lead-lined boxes. Her prolonged, unprotected exposure to the radiation she discovered ultimately caused her death from aplastic anemia, a failure of the bone marrow. Marie Curie's rigorous methodology defined the parameters of the atomic age, and the foundation of modern oncology, a scientific triumph that saved millions of lives at the cost of her own.